The purpose of this video is to demonstrate how we can use Microsoft Excel to plot and properly format calibration data. Throughout this entire series of calibration curve tutorial videos, I will be using the 2016 version of Microsoft Excel for PC. If you are using a different version of Excel, particularly if you are using a Mac, there will be some differences in terms of syntax and keystrokes as you proceed through these tutorials. Nevertheless, it is very important for you to become familiar with these calculations using your version of Microsoft Excel. I encourage you to open the Student Excel worksheet associated with this tutorial and mimic the steps I am going to demonstrate. I recommend having this video open on half of your computer screen and the Student Excel worksheet open on the other half of your screen. You might find it helpful to regularly pause the video after I demonstrate each calculation step to ensure you can reproduce my results using your version of Microsoft Excel. Here I've opened the Excel spreadsheet that includes the instructions and the data associated with this calibration curve tutorial. In this video, we will complete steps 1 and 2 of the 5 steps included in the instructions list. The first step asks us to use the data below to create a scatter plot of blank corrected detector responses, which we'll plot on the y-axis, versus the concentration of acetaminophen, which we will plot on the x-axis. We have 2 columns of data for the calibration standards: the concentration of acetaminophen, which is our analyte of interest, and the detector response associated with each of those calibration standard solutions. The solution that has no added acetaminophen is what analytical chemists would refer to as the blank. The instructions ask us to plot blank corrected detector responses as a function of the acetaminophen concentrations. And so the first thing we need to do is to calculate blank corrected detector responses. I've created a separate column for blank corrected detector responses. If we come down to the first calibration standard, whose concentration is 0.5 milligram per liter, we can calculate its blank corrected detector response with the formula equals, click the detector response associated with this calibration standard, and then we're going to subtract the detector response of the blank. Because we're getting ready to copy and apply this formula throughout the rest of this column, and we always want to subtract this cell corresponding to the detector response of the blank, we need to make this cell reference C18 into what Microsoft Excel refers to as an absolute cell reference. To do so, we can add $ in front of the C and the 18 of the cell reference. Another way that you can do that if you're on a PC, the shortcut version, let me just create this formula again, equals detector response minus detector response of the blank. To make this an absolute cell reference, I can push function F4 when the cursor is beside C18, and you'll see it automatically adds those $, and then I'll push enter. Now I can go ahead and go over and hover over this lower right hand corner of the cell where you see that small square, and if I double left click, it will automatically copy and apply that formula to the rest of the rows. Whenever you copy and paste a formula like that, I encourage you to spot check to see whether that formula was applied correctly. So if I click on, say, the cell for blank corrected detector response here at 6,884 and then select the formula bar, it will highlight the cells that are used in this mathematical formula. And it is, in fact, doing exactly the math that I want it to do. It's taking the detector response of this calibration standard at 22 milligrams per liter and subtracting the detector response of the blank. If I come back up to this cell for our lowest calibration standard, I can left click on the box in the lower right hand corner and drag it up to the cell above if I want to copy that same formula into the first row. So this just indicates that I'm taking the detector response of the blank and subtracting that same detector response. In other words, we can blank correct the blank, and we should, each time we do that, get a 0. We are now ready to plot the calibration data as a scatter plot. In order to do that, I recommend that we select the 2 columns of data that we're interested in plotting. We were instructed to not include the blank as a point in the calibration curve, and so we will exclude that data point from our scatter plot. I'll start by left clicking on the first calibration standard and dragging down so that I select all of the calibration standard concentrations, And then I will push and hold the Control button and click on the corresponding blank corrected detector responses, and again drag down. Next, if I click Insert and then select under Charts the Scatter Plot option, and I'm going to select the option that does not involve connecting the data points with a line or a curve. And our scatter plot appears. And so I'm going to move this so that it doesn't cover the data. So let's just slide it down here. The next thing I want to do is eliminate from my graph some of the elements that are not typically included in calibration curves or similar figures prepared by analytical chemists. And so, for example, the chart title I would like to eliminate, as well as the grid lines. And so if I go over to this plus option, it shows me chart elements that I can toggle on and off. I'm going to turn chart title off, and I'm going to turn grid lines off. The next thing I would like to do is add a trend line. And so if I go back to that same chart elements menu, I'm going to select trend line. And by default, Microsoft Excel will apply a linear trend line to the data. We're quite interested in knowing the equation of this linear regression as well as the correlation coefficient. And in order to get those to be displayed on the graph, I'm going to right click on the line itself and select Format Trend Line. And then a menu will appear on the right hand side that allows me to display the equation on the chart and display the R² value on the chart. I can slide that text box anywhere I'd like, preferably so that it's not covering any of the data points or the line. We can also format this line so that it is more typical of what an analytical chemist would show. And it's uncommon to have a dashed line for a calibration curve. So I'm going to format that trend line and select the formatting options for solid line. And then I'm going to select for dash type solid. And you can pick the color of the line. I prefer to have a black line, and I'm going to take the width down a little bit so it's not obstructing the view of any of the data points. Another element that we need to add to this chart, of course, are axis labels. So if I click again in the chart elements and select axis titles, those titles will appear. And I can edit those titles so that the y-axis would be corrected detector response, which has units of milliabsorbance units times minutes. And the x-axis title is acetaminophen concentration, again with the corresponding units. Another element that we need to add to this figure are tick marks. If I right click on the axis and select Format Axis, I can go down to the option for tick marks, and for major type select Outside. And I can do the same thing on the y-axis. Right click, Format Axis, major type, Outside. As a final step, I'm going to adjust the shape of my graph so that it's approximately square. A graph that's approximately square gives a more accurate visual representation of the mathematical relationship between the dependent variable, which in this case is the corrected detector response, and the independent variable, the acetaminophen concentration. Next, I'd like you to notice that the highest calibration standard appears to be outside the linear range of the rest of the data set. And so it would be typical to exclude this data point from the linear regression if it falls outside of the linear range. In order to do that, we can come up to the data that are selected by the graph. So in order to do this, your graph has to be selected. And then if I grab onto the box in the lower right hand corner, left click, and then lift up one row, that will exclude the highest calibration standard from my graph. The linear regression equation and the correlation coefficient are automatically updated by that change. Because I excluded a data point, I need to communicate to my audience that that data point at 26 milligrams per liter of acetaminophen were measured but just excluded from the linear regression. In order to do that, I can right click on the graph, select data, and then add a data series. So this data series maybe I will call excluded. The series X value, if I left click on this box, it allows me to select 26 milligrams per liter for the X value of the highest calibration standard. And then similarly for the Y value, left click on the data selection box, select the blank corrected detector response for the highest calibration standard, and then select OK, and OK one more time. And what you'll see is that Microsoft Excel now shows that data point as a different color symbol because it is in a separate series of data. I always recommend when you have more than one series of data like this to show not just a different color but also a different shape, so that if someone with a color vision impairment is looking at your graph, they can still tell the difference between one data series and another. In order to do that, I can right click on that data point and select Format Data Series. And then if I select on the bucket of paint that looks like it's spilling and then select Marker Options, I'll select Built-in, and I can pick a different shape, so I'm going to pick a triangle. And now I have a different shape and a different color for the two data series. Next, I'm going to insert a text box that will allow me to create a figure caption for this figure. So let's call this Figure 1. And now I'll just, in the caption, describe what the figure is depicting. I should also add a sentence to the figure caption explaining the difference in the symbol types. And so I've indicated that the red triangle denotes a data point that was outside of the linear range and therefore excluded from the linear regression. We've now successfully plotted the data. We have excluded a data point that was outside of the linear range. And I should mention that when we exclude a data point that's outside of the linear range, just based on this visual interpretation of the data, that should only be true for data points that are either at the highest concentration or the lowest concentration. I can't arbitrarily take a data point that might fall somewhere in the middle of the calibration curve but might be a little bit away from the linear regression and exclude it arbitrarily. I have to have a scientific justification for excluding the data point, and data points that are outside the linear range are either going to be at the highest or the lowest end of the calibration curve. This concludes this video.